Chemical analysis of water. Introduction. Water is one of the abundantly available substances in nature. It contributes about 75% of the matter of Earth's crust. It is distributed in nature in various forms such as spring water, river water, rainwater, etc. Among these, the purest form of water is rainwater. Its chemical formula is H2O. It exists in gaseous, liquid, and solid states. It has the unique ability to support to every kind of life as well as to dissolve variety of substances. So, it is regarded as universal solvent. Thus, it may contain variety of substances either in the form solution or suspensions which can distort the scientific analytical data. Most of these contaminants have the potential to affect not only the number of scientific applications but also create a variety of problems in living as well as non-living systems, i.e., it affects the quality of water. So, to decide quality of water, water analysis is essential. Parameter of water analysis are commonly expressed in milligram per liter, part per million, ppm, etc., where ppm means the number of parts of substance per million parts of water. This unit is also called milligram per liter, mg/liter, or grams per cubic meter. Water analysis includes physical analysis and chemical analysis. Chemical analysis. Chemical analysis of water includes estimation of various chemical parameters of water. Here only total solids, dissolved solids, suspended solids, hardness, salinity, alkalinity, acidity, sulfates, nitrates, dissolved oxygen, chemical oxygen demand, biological oxygen demand are discussed. 1. Total solids. Total solids mean both the dissolved and suspended solids. Commonly potable water contains dissolved minerals while sewage contains large amount of suspended or undissolved matter. Suspended solids, SS. The small solid particles which remain in suspension in water as a colloid or due to motion of water called suspended solids. It is used as one indicator of water quality. Method. 500 cubic centimeters of sample of water is filtered through dried and weighed gauge crucible, W1. Suspended material retains in the crucible. It is washed with distilled water, so as to remove Cl ions. Then crucible is dried, weighed by taking usual precautions, W2. The suspended solids are calculated by using the equation. Weight of suspended solids is equal to W2 minus W1 into 10 raised to 6, divide by volume of sample taken, which is equal to W2 minus W1 into 10 raised to 6, divide by 500, it gives value in ppm. Filtrate is collected along with washings to determine the dissolved solids. Dissolved solids, DS, or total dissolved solids, TDS. Soluble salts of Na, K, Ca, Mg, Fe, and Mn in the form of bicarbonates, carbonates, chlorides, nitrates, sulfates and phosphates etc. are present in natural water and increases the density, affects osmoregulation of organism, solubility of gases and hence it affects use of water for drinking, irrigation, and industrial purposes. Method. Filter 500 ml sample of water through gauge crucible to make it free from suspended matter. Collect the filtrate and washings in a beaker and concentrate to about 50 ml. Transfer it to weighed evaporating dish, W1. Evaporate on hot water bath to dryness. Note the weight of evaporating dish with residue by taking usual precautions, W2. The TDS or DS is calculated by using the equation W2 minus W1 into 10 raised to 6, divide by volume of sample taken, which is equal to W2 minus W1 into 10 raised to 6, divide by 500, it gives value in ppm. Thus, total solids is equal to suspended solids, plus dissolved solids, in ppm. 2. Hardness. Water which does not give good lather with soap called hard water. Hardness is due to presence of salts like bicarbonates, chlorides, and sulfates of Ca and Mg in it. Hardness is divided into temporary and permanent hardness, where temporary hardness arises due to dissolved bicarbonates of Ca and Mg in water, while permanent hardness is due to presence of dissolved sulfates and chlorides of Ca and Mg in water. Temporary hardness is known as carbonate hardness, while permanent hardness is known as non-carbonate hardness. The total hardness is the sum of temporary and permanent hardness. Total hardness of water is expressed in terms of CaCO3 ppm generally. Temporary hardness is removed by boiling the water, while to remove permanent hardness special treatment is essential. Method: there are calculations, titrations, soap and complexometric methods of determination of hardness of water. Out of these, complexometric method is more reliable. Hence it is discussed here. Hardness of water can be determined by titrating known quantity of hard water sample against standard solution of EDTA by using Areotrome black tea indicator at pH 10. EDTA is available as its disodium salt, and it is represented as Na2H2Y, which ionizes as resultant H2Y2, reacts with Ca2 plus and Mg2 plus ions and forms complexes as. Here endpoint is wine red to sky blue. From the burette reading, the hardness is calculated either as CaCO3 in ppm or as Mg equivalent per dm3. It is a total hardness of water. 3. Salinity. Conceptually, salinity of water may be defined as, it is the quantity of dissolved salts in water. It is also called as saltiness. It is measured in generally ppt or percent. It varies from place to place in the ocean, but relative proportions of the most dissolved major constituents generally remain common. The average ocean salinity is about 35 ppt. Rivers and lakes can have wide range of salinities from 0.01 ppt to 0.5 ppt. Dead Sea has salinity greater than 200 ppt. Here note that all natural waters contain some dissolved salts of Na, Mg, Ca. Most common is NaCl constituent, about 91%. It is the main constituent of seawater. The level of salt in water affects its suitability for irrigation, stock, domestic uses, etc. There are two methods of determining the salt content of water, i.e., electrical conductivity, EC, and total dissolved solids, TDS. EC measurement can be done by passing an electric current between two metal plates or electrodes in the water sample, while TDS is a measure of the relative weight of dissolved materials in water sample. Here note that the term salinity is useful to oceanographers. 4. Alkalinity. It is the acid neutralizing capacity, i.e., ANC of water. It arises due to presence of HCO3-, SiO3 2-, HSiO3-, CO3 2-. It is also due to humates. Humate is salt of weak organic acid. Alkalinity due to HCO3- is called bicarbonate alkalinity. Similarly, carbonate alkalinity is due to CO3 2-. Hydrate alkalinity is due to OH-. ANC equals total alkalinity equals HT. HT is equal to concentration of hydroxide ion plus concentration of bicarbonate ion plus concentration of carbonate ion minus concentration of hydronium ion. In natural water, species of boron, silicon, phosphorus, sulfur, etc. contribute in ANC, but their contribution is too small. Hydrate and carbonate alkalinity is also called phenolphthalein alkalinity, as it is determined by it. Bicarbonate alkalinity is determined by methyl orange. So, it is called methyl orange alkalinity. It can be determined by titrating 50 ml sample against 0.02 NH2SO4 solution using phenolphthalein indicator. If necessary, filter the sample and then use. Endpoint is pink to colorless. Then add few drops of methyl orange indicator and continue titration till endpoint is obtained, yellow to red. Total alkalinity, HT, is the sum of phenolphthalein alkalinity and methyl orange alkalinity. Reactions. In first reaction, carbonate ions react with sulfuric acid to give sulfate ion, water, and carbon dioxide. In second reaction, bicarbonate ions react with sulfuric acid to give sulfate ion, water, and carbon dioxide. In third reaction, hydroxide ions react with sulfuric acid to give sulfate ion and water. Phenolphthalein alkalinity at can be calculated as at is equal to N1 V1 divide by V2 into 1000. It gives value in milligram per decimeter cube in terms of calcium carbonate, where N1 equals normality of H2SO4. V1 equals volume of H2SO4 when phenolphthalein indicator is used. V2 equals volume of sample taken. Therefore, H, T is equal to N1, V3, divide by V2, into 1000, it gives value in milligram, per decimeter cube, in terms of calcium carbonate, where V3 equals total volume, phenolphthalein endpoint plus methyl orange endpoint. Alkalinity may be predicted as A. If fraction endpoint for phenolphthalein indicator is 0, then at equals alkalinity may be due to bicarbonate ion only. B. If there is no further titration, for methyl orange endpoint, after phenolphthalein endpoint, then alkalinity is due to hydroxide ion. C. If phenolphthalein endpoint is the half the total titration, then alkalinity is due to carbonate ion. D. If phenolphthalein endpoint is greater than half the total titration, alkalinity is due to both carbonate and hydroxide ions. E. If phenolphthalein endpoint is less than half the total titration, alkalinity is due to carbonate and bicarbonate ions. Alkalinity measurements of water are useful to decide A. Buffering capacity of wastewater and sludges. B. Suitability of water for irrigation. C. The nature of salts presence in water. D. The way for treatments of waste and natural water. E. It is also useful to calculate Langmuir saturation index. Here, note that soft water obtained by orthophosphate treatment does not obey these rules. Instead of H2SO4, only strong acid like HCl can be used. 5. Acidity. Acidity is the power of water to neutralize a hydroxide, ions. It is expressed in terms of calcium carbonate. Acidity arises due to pickling liquors, acid mine drainage, industrial effluents, humic acid. Acidity of water can be decided by titrating water sample with standard solution of NaOH. Methyl orange endpoint, pH 4.5, measures the acidity due to minerals and CO2, while phenolphthalein endpoint, to reach pH 8.3, determines the total acidity. Mineral acidity. Here known quantity of water sample free from chlorine is titrated against 0.02 NaOH using methyl orange indicator. Total acidity at room temperature. Here water sample is titrated against 0.02 NaOH using phenolphthalein indicator. Total acidity at boiling temperature. To water sample add phenolphthalein. Boil for 2 to 3 minutes and titrate with 0.02 NaOH. Acidity as calcium carbonate is equal to centimeter cube of 0.02 normal NaOH into 1 into 1000 divides by centimeter cube of water sample taken for titration. Note that methyl orange acidity indicates mineral acidity. If mineral acidity is absent, then total acidity is CO2, carbon dioxide, acidity of sample. Phenolphthalein acidity is the total acidity of the sample water. 6. Sulfate. Natural water generally contains sulfate. Mine drainage wastes also contain high quantity of sulfate due to oxidation of pyrites. If potable water contains Na2SO4 and MgSO4 beyond the prescribed limit, it may cause cathartic action. It may be estimated gravimetrically, colorimetrically, turbidimetrically, titrometrically. Here gravimetric method of sulfate estimation is discussed. Gravimetric method. In this method sulfate is precipitated as BaSO4 by the BaCl2 solution, precipitating agent, in acidic, HCl, medium. Precipitation is carried out near the boiling temperature, then the precipitate is filtered and washed with hot water to get free from Cl, chloride, ions after digestion. Lastly, this precipitate is ignited and weighed by taking usual precautions. 7. Nitrate. It occurs in ground and surface water, wastewater treatment plants, natural water distribution systems, etc. It is the end products of decomposition of organic matter. Wastes from fertilizer manufacturing plants introduce nitrate in water system. It is also produced by aerobic stabilization of organic nitrogen. Its maximum admissible concentration, MAC, is 50 mg/liter. If its concentration in water supply exceeds this limit, then it has hazardous effect to health, dangerous to infants, below the age of 6 months, causes a child disease, methemoglobinemia, etc. So, it becomes essential to monitor nitrate regularly in water supply. There are several ways to estimate NO3. One of the simple methods is discussed here. I.e., in water sample phenol disulfonic acid and KOH is added, the color so formed is used to determine the concentration of NO3 in ppm. By comparing with standard colors. In spectrophotometric method, the concentration of nitrate must be below 5 ppm or made so by diluting water sample. 8. Dissolved oxygen, DO. It is understood that dissolved oxygen in water is the index of physical and biological processes going on in water. Water free from pollutants gets saturated with oxygen, O2. There are two ways by which oxygen, O2, get dissolved in water. 1. Diffusion/absorption from air. 2. Due to photosynthesis in water by vegetation. Dissolved oxygen, DO, may be defined as the amount of oxygen dissolved in milligram per dm3 of water at fixed temperature is known as dissolved oxygen. Oxygen dissolves in water slightly and is important for aquatic life. 4 to 6 milligrams per dm3 of DO is the optimum value for good water quality, which ensures healthy aquatic life. Lower values of DO indicate water pollution. Example: within 4 to 5 ppm DO, fish becomes rare. Further decrease in DO causes migration of aquatic fauna and plant or death. There are different methods used to decide DO. Here membrane electrode method is discussed. It consists of Makareth oxygen cell. In this cell Ag and Pb electrodes are dipped in saturated KHCO3 solution. These are separated by using polythene membrane, 0.06 mm thick, from solution of sample test. Then galvanic cell is plugged of pH meter. It gives direct DO reading in mg/dm3. Here readings are recorded for sample solution, standard, and blank. At negative electrode, silver, Ag, 2 water molecules and 1 oxygen molecule, takes 4 electrons from electrode and forms 4 hydroxide ions. While, at positive electrode lead, Pb, 2 lead atoms react with 4 hydroxide ions and releases 2 electrons on electrode and forms 2 molecules of lead hydroxide. 9. Chemical oxygen demand, COD. It is the index of total organic content of water oxygen demanding substances in water. It may be defined as the total amount of oxygen required for oxidation of substances is known as chemical oxygen demand. It is based on the assumption that all organic matter can be oxidized by strong oxidizing agents in acidic media. A variety of oxidizing agents are used, but potassium dichromate is the best for this purpose. COD is more scientific term than the term BOD. Further, it is reproducible. It is expressed in ppm. Determination of COD. The known quantity potassium dichromate, K2Cr2O7, is added to the measured amount of sample. Mixture is boiled with concentrated sulfuric acid, H2SO4. Then excess of dichromate ion Cr2O72 determined by titrating with standard ferrous ammonium sulfate solution, back titration. Indicator used is ferroin. As per need silver sulfate, Ag2SO4, mercuric sulfate, HgSO4, etc. are added to the solution. Difference between back and blank titration gives amount of dichromate consumed in oxidation of organic and inorganic matter. Thus, COD in milligram per decimeter cube is equal to B minus T into N into 1000 into 8, divide by volume of sample taken, in centimeter cube. Where B equals blank reading, T equals back reading, and N equals normality. COD is useful 1. In management and design of treatment plant. 2. To determine the efficiency of treatment plants. 3. To study industrial waste. pH of water, nitrification process, toxic materials, and type of microorganism affect the BOD test, but COD test is not affected by these factors. 10. Biochemical or biological oxygen demand, BOD. Nowadays we are facing burning problem of water pollution. BOD determines degree of water pollution. Hence study of BOD of water becomes prime important. BOD may be defined as the amount of oxygen required for the biological oxidation of organic material in water during 5 days under controlled conditions, 293 K, is known as biochemical oxygen demand. This is empirical parameter for organic matter in water. To get BOD value one has to wait for 5 days. The values are not reproducible. It is expressed in milligram per dm3 oxygen or in ppm. For potable water it must be less than 1 ppm. The substances decomposed in the BOD test may be the chemicals readily attacked by oxygen, O2, such as sulfides, sulfates, sulfides, readily oxidizable compounds, ferrous ions etc. and food used by microorganisms. The food of microorganism may be nitrates and phosphates, which is found in domestic sewage, waste from animal feed lots, packing plants, farm wastes containing excess fertilizers etc. Increase in microorganisms increases value of BOD. High value of BOD is deleterious to aquatic lives. The determination of BOD is useful to determine 1. Degree of pollution of water. 2. Efficiency of wastewater treatment plants. 3. Self-purification capacity of water body. 4. Possible control measures of pollution. 5. Pollution load of wastewater treatment on environment. 6. Kind of organisms present in water. Determination of BOD. To determine BOD, BOD incubator, BOD bottles, and allyl-thiourea solutions are essential. To prepare allyl-thiourea solution, 500 mg allyl-thiourea dissolved in distilled water and diluted to 1 dm3. Method. Take known quantity of sample. As per need, adjust pH of sample to 7.0 by using 1 normal NaOH or 1 normal H2SO4 solution. To avoid loss of oxygen during incubation, dilute the sample as per need. Now fill the 2 sets of BOD bottles. Add 1 cubic centimeter allyl-thiourea solution to each bottle and stopper by taking usual precautions. Determine DO in one set immediately by using membrane electrode or any other method. DO. Incubate the other set in BOD incubator. After 5 days measure the DO, D5. And BOD in milligram per decimeter cube is equal to D minus D5 into dilution factor. Here note that BOD is indicator and not pollutant.